Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistants, and today we are looking at vapor pressure and temperature. And we have a few problems that we're going to go through, kind of work through the process of how to do problems of these nature. So we're asked to calculate the vapor pressure for a solution made by dissolving 182 grams of glucose, which is C6H12O6, if you don't know, in 640 milliliters of water at 40 degrees Celsius. We're asked what is the vapor pressure lowering given the vapor pressure of pure water at 40 degrees Celsius is 55.32 millimeters of mercury. So what we need to do is select the proper formula and identify the components that fit that formula. So the proper formula is P pressure, the vapor pressure lowering, is equal to X, which is your mole fraction, P naught sub 1. And for this, we already have our P naught sub 1, which is 55.32 millimeters of mercury. What we need to find is our mole fraction. And in order to do that, we need to calculate the moles of the various substances. So we need to find the moles of water, and our moles of glucose. And I'm just going to call it N sub W and N sub G going forward. So moles of water, we're given the volume of water, and knowing the volume of water and the density of water, we can solve for the mass of water, and from there we can find moles. So we're given 640 milliliters, and the density of water is approximately 1, so let's put 1.00 grams per milliliter, and that should give us grams. And then we're going to multiply that by 1 mole over 18.02 grams, which is essentially dividing by the molar mass. So you'll find that milliliters and milliliters cancel out, grams and grams cancel each other out, and you're left with moles. And that ends up being 35.5 moles. Glucose is a little more direct. We have 182 grams times 1 mole over 180.2 grams, which is 6 carbons plus 12 hydrogens plus 6 oxygens. When you add up all their molar masses, it gives you 180.2 grams per mole, and we're simply dividing by that, so it's like multiplying by the reciprocal. And that gets us 1.01 moles. Then our mole fraction is going to be our moles of water divided by the moles of water plus the moles of glucose, which is going to be 35.5 moles over the sum of the two that we just solved for, which would make it 36.51. Or you could just say 36.5. And that gives us 0.972. This is a unitless expression, because the 2 moles canceled each other out. And the result after you've put it back into the original equation, we're trying to find pressure. So it's our mole fraction, 0.972, times our P naught sub 1, which is 55.32 millimeters of mercury, which gives us 53.8 millimeters of mercury. Let's take a look at another problem dealing with vapor pressure and temperature. We're asked to calculate the freezing point of a solution containing 516 grams of ethylene glycol in 5,025 grams of water, with the molar mass of ethylene glycol being 62.07 grams per mole. So we need to find the freezing point of the solution. So what we're looking for is delta T sub F, which is equal to K sub F times the molality. So we need to figure out the molality of ethylene glycol in this solution. So in order to do that, we need to find the moles of the solute, which is going to be given from the 516 grams, divided by the mass of the solvent, which we are already given. But we are given it in grams, and we need to simply convert it to kilograms. Divide this by 1,000, and you end up with 5.025 kilograms. Okay? So let's solve for moles of ethylene glycol. So N is going to equal 516 grams times 1 mole over 62.07, 62.07 grams. And that'll get us the moles of ethylene glycol, 8.31 moles. Then to find the molality, we simply take the moles of the solute, 8.31 moles, and divide by the mass of the solvent in kilograms, which is 5.025 kilograms. And that gets us 1.65 molal. So taking that and plugging it back into our expression, what you would need to do is, we're not given our K sub F, but K sub F is a constant, and it is available in your book. And if you look it up, for freezing, water's K sub F is 1.86, or edit. For freezing, ethylene glycol has a K sub F of 1. For freezing, our K sub F, if you look it up in the book, will be 1.86 degrees Celsius per molal. And then you could similarly look up, this is K sub F. You can also look up K sub B if we wanted to look at the boiling point, which is equal to, let's see, in your book it says 0.52 degrees C per molal. So let's do both. Let's find both the freezing point and the boiling point. So, knowing this for ethylene glycol, we can find that our delta T sub F is going to equal 1.86 degrees C per M times 1.65 molal, which gives us 3.07. 3.07 degrees Celsius, because our molals canceled out. So what does that mean? Well, we're going to take, because the solvent is water, we're going to take our freezing point of water in Celsius, which is 0, and we're simply going to subtract our 3.07 degrees C, which gives us negative 3.07 degrees C. What does that mean? Well, that means at this particular concentration of ethylene glycol in water, it will freeze at negative 3.07 degrees Celsius. If we were to do the same thing for boiling, we could take delta T sub B, and that's going to be K sub B times the molality. So that's going to be 0.52 degrees C per molal times 1.65 molal, which will give us 0.858 degrees C. So, comparing that with the boiling point of water, which is 100 degrees Celsius, you simply add your delta T sub B, which is 0.858 degrees C, which gives us a boiling point of 100.858 degrees Celsius. Let's look at one more problem dealing with temperature and solubility. We're given the problem a 15.9 gram sample of a substance with the empirical formula of C7H5 is dissolved in 305 grams of benzene. The freezing point of the solution is 1.50 degrees Celsius below that of pure benzene. What is the molar mass and the molecular formula of this compound? And this may seem like a very complicated problem, but again, we're gotta get back to what we know. And what we know is we know our change in temperature of freezing, so that's our delta T sub F. We're given that it's 1.5 degrees Celsius below that of pure benzene. So it has to be compared with the pure substance in order to get a full picture of what we're trying to do. If it gave just the temperature, then you would have to assess where that temperature lays when compared to that of the pure substance, in this case benzene. So that'll be our delta T sub F. Now our K sub F is something that you would have to look up in your book. And every substance has its own K sub F and K sub B. For benzene, it is K sub F is going to equal 5.12 degrees Celsius per molal. So knowing that, we can then solve for the molality relatively simply. So if delta T sub F is equal to K sub F times M, then molality M is equal to delta T sub F over K sub F, which in this case is 1.50 degrees C over 5.12 degrees C per molal, which gives us a concentration of 0.293 molal. Then we can take what other information we're given and look at that and see how far we can go. So what we can get from molality other than through this equation and its corresponding equation for boiling, we can also get the moles of the solvent, or the mass of the solvent, and the moles of the solute. And in fact, we are given the mass of the solvent. So that's a clue that we probably need to also find the moles of solute. And from the moles of solute, we might be able to find what it is that we're looking for, which is the molar mass and molecular formula of the unknown substance. So if we take our mass of solvent in terms of kilograms, which would be, we're going to say moles are going to equal 0.305 kilograms. And we're going to multiply it by the definition of molality when compared to our previously calculated value, which would be 0.293 moles for every 1 kilogram. And you'll note that kilograms cancel each other out, and you're left with moles, which would be 0.0894 moles. So now we have the number of moles. And what else do we have? We have the mass of the solute right here, very first thing. So what is molar mass? It's simply grams per mole. So looking at that as sort of a unit definition of it, we can then solve for the molar mass of this particular substance, which would be 15.9 grams divided by 0.0894 moles. And when you do that out, you find that the molar mass is going to be 178 grams per mole. And then from here, we know what our molar mass is. That's the first part. That's the part, first thing we're asked for is the molar mass. That's what is the molar mass. We're also asked what the molecular formula of this compound is. So we need to look at how we can take molar mass and convert it into a molecular formula. Well, we have the empirical formula right up here. So if we take our C7H5 and we calculate the molar mass of that, we'll find that that equals 89.11 grams per mole. So if we take our 178 grams per mole, and we simply divide by the molar mass of the empirical formula, 89.11 grams per mole, we'll find that it approximately equals 2, which simply means that we need to multiply all the components by 2, which gives us an empirical formula of C14H10. 7 times 2 is 14, 5 times 2 is 10, and if you were to research that, you'd find that it's called anthracene, which is a joined ring structure.